To start off today's lesson, we're going to be looking at a small little problem or scenario that will lead into the topic for today. So what we're going to look at is cracking into a safe. So a safe is secured with what we call a binary lock, or it's one example of a type of lock, which consists of several switches. Each switch has two positions, up and down. The safe can only be opened when each switch is set to the correct position. The more switches on the lock, the more difficult it is to crack. So we want to complete the following table to find the relationship between the number of switches in the lock and the number of possible settings. When listing the possible settings, we're going to use a sequence of U's and D's to represent the positions of the switches. And we've done the first one already here. So if we have one switch, we either have it as up or down, which means there's a total of two settings. If we look at example or two switches, we have multiple options. Our switches are either up and up and down and up, and both down. So when we have two switches, we have four possible settings. So what I want you to do is try to go through and determine how many switches or how many settings there are for 3 switches and 4 switches. And then we're going to come back and we're going to take a look at the relationship between the number of switches and the settings. Right, if you can get through and you recognize that, again, you can try to figure out how many possible settings there are when you have a 10-switch lock. So coming back to our table, this should be all the positions that we've found for the different number of switches. Right? We did 1 and 2 together. We'll look at 3. So 3, you should have found 8 possible settings. All up, up, down, up, down, up, down, up, down, up, down, down, and down, down, which gives us a total of 8 settings. When we add a 4th switch in there, you should find 16 settings. So you can take a look at these possible settings. I'm not going to read through all of them because it'll just sound like a bunch of stuttering, or it just might sound like old dial-up internet. But take a look at all 16 settings. Make sure or check to see if you found the same ones or if there's any that you missed. But we should find that there are 16 settings. Now, if we added a 5th switch, or a 6th switch, 7th, 8th, even as our question suggested down here, a 10th switch, how many settings would there be? Now we can see by going through just 2, 3, and 4, it tends to get very tedious and impractical as it mentioned. So is there a pattern that we can see here that makes it easy to determine the number of settings based on the number of switches? And if you can think about that pattern, think about, okay, how can I quickly calculate that? That's going to be the topic of our lesson today. And if you think about it, maybe what you may have come up with is that these number of settings are all multiples of 2, and it does relate to the number of switches. I have 2 settings for 1 switch, 4 for 2, 8 for 3, 16 for 4. Right? There is kind of a pattern here. And the pattern is, it's 2 to the power of, we could say, 2 to the power of the number of switches. So if we look at the first example, 2 to the power of 1 equals 2. 2 to the power of 2 equals 4. 2 to the power of 3 is 8. 2 to the power of 4 is 16. So basically what it's saying is, for every switch, I have two options, and I'm going to multiply that by 2 every time by the number of switches. So if I think of 5 switches, I'd have 2 options for the first one, multiplied by 2 options for the second, multiplied by 2 for the fourth, and finally 2 for the fifth. Right, because we have up, down for our 2 settings, up, down, up, down, up, down, up, down, which works out to 2 to the fifth, which works out to 32 possible outcomes. And again, if you went through and you listed them out, you would find that there are 32 possible outcomes there. So how many possible settings are there for a 10 switch lock? Well, you do the same thing that we just did. There's 2 options for each switch, right, up and down, to the power of 10, because we have 10 switches. So it's going to be up, down for the first one, multiplied by up, down for the second one, and so on. So this would work out to 1,024 possible settings. So again, mathematically it's very easy to figure out, but if you had to go through and list every one of those settings by hand, it would take you quite some time, and you'd probably get them mixed up, and there's a chance that you probably forgot one of the switches, or you miscounted, or you just got confused by all the ups and downs. So having or recognizing this kind of pattern is very helpful when dealing with these types of questions. So what our lesson is going to focus on today is powers. Right? So that was the idea of powers, right? So we have seen that to calculate the number of settings for a particular number of switches, we must repeatedly multiply by 2. And we kind of walk through the reason why. And powers are used to represent such operations as we see here. 2 to the power of 10 equals basically 2 multiplied by itself 10 times. Each power consists of a base, which is the value being multiplied, and the exponent, the number of bases being multiplied together. So we have our base is 2, that's what's being multiplied, and it's being multiplied 10 times, or together 10 times. All scientific calculators have a specific key for evaluating powers. There's a couple options that we see here that you might have on your calculator. X to the power of y, a to the power of b, or just this little hat symbol. So regardless of how it works, you would say, for example, you would write 2, press the XY button, and then your exponent of 10. Or 2, then the AB button, and then the power of 10, or 2, the little hat, or the arrow to the power of 10, and that would give you your answer. If you're using an iPhone, again, I recommend that you don't, but it is the XY button. The reason, again, I recommend why you don't is just, again, it's a little bit more confusing or more difficult to use the iPhones once we get into larger calculations. And you do have to turn it on its side to get the scientific notation. So, going through, just practice making sure that you can use the exponent button on your calculator. Do 2 to the power of 10 and see what you get. Well, we already kind of did that on the last page, but again, just go back and double check, and you should find that it is the 1024. So many expressions involve powers where the base is a variable in terms of our letter, or in terms of our power. So the base, the thing that we're multiplying together, is a letter or a variable. And we should be familiar with using powers for area and volume, which we will be looking at later on in the course. So if I wanted to find the area of a square, right, generally speaking, a square, all sides are the same, side times side. So we could write area is length times width, but for a square, we know that they're the same, so we could say side times side, but instead of writing it out like that, I could just write area equals side squared to represent side times side. Same with volume, especially for volume for a cube, because again, for a cube, all sides are the same. So volume for a cube or any rectangular prism, length times width times height. They're all the same measurement, so I can do A times A times A. Or in this case, because I have 3 A's multiplied together, I can write A to the power of 3, just to simplify that. So in our binary lock, each switch just had 2 possible positions, right? Up and down. But we could also create locks using switches that have 3 or more switches. So for example, the sequences of ridges on keys, so your normal house key, vary in height, right? If you have a key, you can take a look at it and you can see that the ridges vary in height, and those represent a code of switches. Right? That kind of determines when you plug it in, or when you put the key into the lock, it kind of puts the switches at different heights, which is the code which unlocks it. So suppose a key has 8 ridges, or you could say 8 switches. And each rid can be one of 3 possible heights. How many distinct keys can be made using this method? So if we're only limited to 8 ridges, and each ridge had one of 3 possible heights, how many different keys or different settings, going back to the last example, could we have? So similar to before, right, our base represented our number of outcomes, or number of outcomes, or a number of options, you could say. And our exponent, the small number that we raise it up to, was the number of switches. So in our case, we have 8 ridges or 8 switches, and we have 3 options for each switch. So in our case, we're going to have 3 to the power of 8, right? Because it's going to be, say, high, medium, and low for one switch, high, medium, and low for another switch, high, medium, low for the third, and so on. So the value, or the number of possible settings, if we have 8 ridges and 3 possible heights, is going to be 3 to the power of 8, which works out to 6,561. So we can see that it's a lot easier to use powers to solve this rather than try to go through and visualize every single possible setting or possible key. This also applies to the digital age, right? So this also, again, we talked about binary switches or binary locks and keys, still useful, but physical locks can be picked using trial and error since there are relatively few settings that you could have, right? If you're cutting a key, there's really only so many heights that you could use. If you have a switch, again, there's only so many possible settings that you could have, right? So you're limited due to the physical nature of those locks. Digital codes such as passwords, PIN numbers, and encryption keys have many more possibilities because you're given so many different options, right? If we consider a 4-digit PIN card with our 4-digit PIN card, each digit has 10 possibilities, right? If we want to write those out to visualize them, our number or a single digit could be 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. So there's 10 possibilities there. How many different unique codes are possible? Right, so again, if we go back to the same kind of situation that we were looking at before, the base was the number of options. Right? So how many options do I have for a pin? Right? So I have 10 options because there's 10 possible digits, or 10 possible numbers, sorry. The exponent is going to be the number of, in our previous examples, the number of switches or the number of times I'm going to be using the 10 digits. So if I think of a PIN card, I have 1, 2, 3, 4 spots that I need to fill, or you could say 4 switches or 4 ridges, however you want to kind of visualize it. So that means I'm going to have 10 options for the first one, 10 options for the second, 10 for the third, and 10 for the fourth. So it's going to be 10 to the power of 4, which is going to tell me the number of options. So again, rather than going through and putting out or visualizing or writing out every single PIN number, I can just mathematically do it and see that there's going to be 10,000 possible codes. So that's just for a PIN card, right? That's just for, say, a bank card where there's more security and encryption within the card that makes it specific to you. But you can imagine if you stole someone's card, unless you had a reader or you had some way of going through and using a computer to calculate every single possible code, it would probably take you some time to try every single one, and chances are it would be locked out by then. But even with this, if you think about it, if you try to get a computer to go through and manually come up with every single number, right? A computer could probably run through all the possible codes fairly quickly, right? So there are cases where when you think of a code or you think of a password, right, that changes, right? So it changes where it's asking for letters. So you're using, say, a certain number of letters, and you have to involve characters, right? So that adds more options. Maybe you have to involve letters, characters, and numbers. There's even more options. Uppercase and lowercase adds in another set of number or letters, right? So by adding in all of those possibilities, it just creates more possible codes or options. So moving on, so to ensure security and privacy for things such as emails or banking transactions, digital information is encrypted using codes or keys that have an enormous number of possibilities. So for an example, a 64-bit encryption key has 2 to the power of 64 possible values. Right? So this is basically saying there's 2 options, and then there's 64, say, switches that you would have. So if we were to calculate what this works out to on your calculator, you might get something a little bit different. So in our case, if you try this on your calculator, you should get something similar to, say, 1.844. I'm going to round the 6 up to a 7, and it might, depending on what it says, it might say E19 or 1.8447 times 10 to the power of 19. Again, depending on your calculator, it might visualize a little bit different. It might look something like that. You might actually see the exponent of 19. The E in this case just means multiplied by 10 to the power of whatever number comes next. So basically these two expressions are the same thing. Basically what this is saying is that since the result is so large, our calculator cannot display it. There's not enough numbers or enough spaces on our calculator to actually put this number down in its traditional form or in the standard notation. Most calculators can only take up to 10 digits, and large numbers like this are expressed in scientific notation. So that's going to be the second part of the lesson, because if we use powers chances are we could get to numbers that are expressed in scientific notation. So a number in scientific notation takes the form m times 10 to the power of n, where m is a decimal value between 1 and 10, and n is an integer, so basically any number or any whole number. It could be positive or negative as well. The number of decimal places included in m depends on how much accuracy is required. And what I'm actually going to do, I'm going to go back and we'll actually color code this a little bit. So m is the decimal value. So in our examples here, they were these two spots. And n is the integer, which was the 19. Again, depending on how your calculator visualizes it, you may not see the times 10, as long as you recognize that e represents times 10 to the power of n, our integer. The number of decimal places, again, as we said, depends on the accuracy required. We don't need to include all of the numbers because generally speaking, you get a sense of how large the number is anyways. The most important thing is to say maybe 3 decimal places and then the exponent after. That's the key part. So consider the value above. They've actually rounded it here to 1.845. So they've kind of kept fewer decimal places than we did. To express this number in scientific notation, we use the property that multiplying a number by 10 shifts the decimal place to the right one place, or for integers, basically adds a 0 at the end. In this example, we need to multiply 1.845 by 10 19 times. Since there are 3 decimal places, that means we will need 16 zeros, or 19 minus 3. Right? And the reason is, when we go through it, the 3 decimal places take up a 0. So 1, 2, 3. Now we're at a whole integer, which basically then means we have 16 zeros after it, which is the number we get here. So can you think of other applications where you might need to use scientific notation, or where it's necessary to express very large numbers? Right, so take a second to think about this, or see if you can come up with other applications, other areas, or other subjects even to start off where scientific notation is necessary. Right, where are we going to be dealing with numbers so large that we can't write them out, or it's not practical to write out a number that large? I can't even begin to think about what number that would be, because it's more than 1 billion and I'm not sure what's beyond that. So as a practice, we're going to go through and complete the following table to think about, just to get used to using scientific notation, understanding what it means. So 4.23 times 10 to the power of 6. So that means I need to move the decimal place 6 spots to the right. So if you're struggling with that idea of moving it to the integer and then just adding zeros, you could write 4.23 and then start moving your decimal place. 1, 2, 3, 4, 5, 6. So that means I have 4 spots that are missing where I have to add zeros in, and that gives me my number. So again, that's the same idea of I have 2 spots to move it to get it to a whole number. 6 minus 2 is 4, which means I have 4 zeros to fill in. So again, your answer, regardless, at the end should be 4, 2, 3, 1, 2, 3, 4. So 4,230,000. So again, different ways you could represent it, or different ways you could figure it out. Whether it's the 4.23, 1, 2, 3, 4, 5, 6, and then fill in our zeros to get to that point. Our next one, we want to convert this to scientific notation. It's a little bit too large to write out every time. We know our first number is going to be a decimal, so 5.26. Now we need to think about, well, the decimal after any whole number is right at the end. So you could think about, well, how many spots am I moving it up? Right? So you could actually go through and physically count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So because we moved it 11 spots, that's 10 to the power of 11. You could also think about, well, I can see right here there's 9 zeros and then 2 more spots to get to the 5. That's 11. So 9 plus 2 is 11. Or again, you can actually go through and physically count the spots. 1.432 times 10 to the power of 8. So again, depending on how you're comfortable doing it, you might say, okay, well, there's 3 decimal places. 8 minus 3 is 5. So that means there's 5 zeros I have to add on to the end. Or, if you're more comfortable actually moving the numbers, you can do that as well. So the decimal's here. I'm going to move the decimal to the right 8 spots. 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to put in zeros in every missing spot, which still works out to still out to 5 zeros. And then our last example, we know it has to be a decimal, so it's going to be 3.2 times, and then we could count, so there's 3, 6, 9, 10, 11, 12 spots or 12 positions or placeholders before the 3. So it's going to be 10 to the power of 12. Or again, the decimal after any whole number is at the end. So you can count going forward. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that decimal is going to have to jump 12 spots, which means it should be 3.2 times 10 to the power of 12. So again, that's just a bit of a review, maybe a bit of a review of powers. Hopefully gave you a little bit more information on how passwords are created now because of the use of powers. And we touched a bit on scientific notation. So just make sure you're comfortable converting or understanding what a number in scientific means in standard notation, and make sure you're comfortable with exponents and how to use them, especially when it comes to locks, because again, that's probably one of the more practical uses of them.